Making decisions based on intelligent information processing is something we're constantly doing. Most of us have no idea about the complexity of information processing that we do in our everyday life. So when I look at that photo and think, do I know that person? Or decide, is this sound coming from my phone or my microwave? Or what are the sequence of muscle movements that I need in order to pour this glass of champagne? These are all situations that require highly complex information processing. And we use this information processing to make future decisions. Here, when I say decisions, I don't necessarily mean a conscious decision. Knowing the sequence of muscle movements that I need in order to pour a drink or get up from a chair. These are not conscious decisions, but they are choices that I'm making at each moment in time. In fact, it's usually the things that we do without thinking that are the most difficult from an information processing point of view. For example, think of a task that you might traditionally consider difficult, like calculating 67 squared in your head. Well, from an information processing perspective, something that we consider trivial, like recognizing your friend across the street, is incomparably more difficult than calculating 67 squared. Just walking around, putting on clothes, going to groceries, what we do in these everyday activities, we're processing information to a capacity that far exceeds still the most powerful algorithms and computers that we have right now. Now that we've discussed human intelligence, let's talk about what is artificial intelligence. One definition of AI is its computers accomplishing tasks that mimic human intelligence. So this means that in order to build AI, we're going to have to be able to explicitly specify all the information processing problems that underlie this intelligent behavior that we take for granted. When designing AI, it's useful to think, what information processing problem do we want the AI to provide a solution for? So I'm going to be illustrating this by going through a bunch of intelligence domains and showing you an example problem that we can get the AI to solve in each domain. For processing images, we might ask the AI, what's the object in that image? For sound processing, we might ask the AI, what made that sound? For speech recognition, we would ask, what word was that? For language comprehension, we would ask the AI, what was the intention behind that sentence? For playing games, we could ask, what's the next best move? For robotic movement, we would ask, what is the sequence of joint positions that can execute this action? For navigating environments, we would ask, which direction to go next? These are just a small number of the very, very vast number of questions that we can get AI to provide solutions for. So now let's revisit our original definition of AI and expand on it. Originally, we had said AI was tasks requiring human intelligence being accomplished by machines. I'd like to expand on this by describing AI as a model that maps inputs to solutions that can generate intelligent behavior. Here I'd like to add that this mapping from input to output can happen on vastly different timescales. For example, for a robotic arm, each millisecond the AI is taking in new input representing the environment and outputting a new position for the position of the robotic joints. In contrast, at the other end of the input-output timescale would be something like supply chain analysis. This analyzes the process of taking raw materials to finished products. A supply chain model might take in as input all the different data involving all the different factors such as warehouse, managers, logistics, weather, product, and so on. Supply chain analysis is extremely data intensive. It easily uses hundreds of terabytes of data. The model will simulate how the different components of data all might affect each other under different conditions, and then take all day to process this information before it gives a single output for the estimated cost of a shipment. One more thing I'd like to add is that the outputs AI produces are usually considered predictions, because the tasks that we consider intelligent are usually so complicated that the models don't have certainty about what the actual answer is. Also, the world is always changing, and we're never completely sure that the future is going to behave like the past. What is the relationship between AI, machine learning, and deep learning? These are all forms of AI, which means they are all models of how inputs map to an output that is some solution to an information processing problem. A model maps inputs to outputs by receiving some numerical representation of input and applying some computational algorithm to this input in order to produce an output. For example, if we wanted to model an AI doctor that finds the correct dosage for medicine, we would take input describing patient information. The model would then apply a computational algorithm to this patient information in order to produce a recommended dosage for medicine. In traditional AI, the computational algorithm would be fully specified beforehand. For example, we would pre-specify that the dosage would be 1 times the number of coughs per minute, 0.03 times the temperature, and 0.2 times the body weight, all summed together. Machine learning and deep learning, which is a type of machine learning, are types of AI where the models learn the computations for mapping inputs to outputs. The model is given some initial idea for the general mathematical forms used in its computations. However, the exact numerical values in these computations are left unspecified. For example, for our AI doctor, we might say the general form of the computation will be some number times number of coughs per minute, plus some number times the temperature, plus some number times the body weight. Learning is the process where the model finds the exact numerical values for these numbers to be used in the computation so that the model can most successfully map inputs to appropriate outputs. During the learning process, we train these models by providing them with training data, which means we give the model many examples of inputs, and we also specify the criteria for what makes good outputs in response to this training input. For our AI doctor, we give the model many examples of patient information data, and here what makes a good output would be the correct corresponding dosage. The model would then use a learning algorithm to find the exact number for each of the multipliers specified in the mathematical form that we had said the computation would take. The model would then find, for example, that you need to multiply the number of coughs by 1, you need to multiply the temperature by 0.03, and the weight by 0.2, and these values would be learned from the data. Models need to not just produce accurate outputs for its training data that it's already seen, but also models need to be able to extrapolate from the training examples to produce appropriate outputs for new inputs that it's never seen before. Deep learning is a type of machine learning where the computations are in the form of a neural network. A neural network is a type of model composed of many individual computing units, also known as neurons. Each neuron applies very simple computations to its inputs, involving just multiplying, adding, and passing sums through simple filters. These simple computations of many individual neurons are coordinated into the combined computations of a large multi-neuron neural network. Deep learning is more flexible than traditional machine learning in the mappings that it can achieve between inputs and outputs. And also, we don't need to pre-specify what features in the input data it needs to pay attention to. I'll be giving more examples of this difference between deep learning and machine learning to make this more concrete in the coming lectures.